Hello, best and brightest. I hope you have found your day relaxing and a good recharge before the end of the quarter. I thought I could do this AB calculus velocity and other rates of change homework for you. I know some of you still had questions on it, and it might be a good day for you to watch this. So this first question talks about a rock thrown vertically upward from the surface of the moon at a velocity of 24 meters per second. So we know it's going up. It reaches a height of, and this is a position function. Remember, usually this year when you see S or X with a T, so S of T or X of T is usually a position function, and this is given to you as 24T minus 0.8T squared meters in T seconds. So we're going to find the rock's velocity and acceleration as functions of time. Take the derivative. There's V of T. So V of T is going to equal 24 minus 1.6t. We took the derivative. All right, the derivative of position is just velocity. If we want to get the acceleration, which it's also asking us for, what's the acceleration? Take the derivative. The derivative of velocity is acceleration. That's negative 1.6. And there's our constant, that negative 1.6. Remember on Earth, we found out, this is the same idea as when we did the problems and we had the negative 9.8 out in front. How long did it take the rock to reach its highest point? And you can think about it this a few different ways, but the way I'd like you to think about it, and you can logic your way to this a number of different ways, okay? But one way you can think about when it's at its highest point, you know the rock is going to go up, and then it's going to go down, come down. So one way to think about this, kind of the calculus-y way to think about this, all right? And you can certainly, by the way, logic your way to this in other ways, but one way you can think about this is it's going to be when the slope of the tangent line is equal to 0. So here I can get my slope of the tangent line. Oh, wait, that's just velocity. So my height, my highest height is going to be when my velocity is equal to 0. So I just have to set this equal to the velocity equation. If I solve that, I'm going to get at 15 seconds. At 15 seconds, this thing is going to reach its highest point. So it's going to be when the velocity, or the derivative, is equal to 0. The derivative of the position is the velocity. How high did the rock go? Well, when is it going to reach its highest point? We just figured that out. It happens at 15 seconds. What is its position at 15 seconds? Its position at 15 seconds is going to be given by plugging the 15 into that position function. So we can do 24 times 15 minus 0.8 times 15 squared. That, I think it came out to 180 meters. When did the rock reach half of its maximum height? Now this is just solving this equation. This is going back to algebra 2 and saying, when is the height 90? When is the position function equal to 90? That's what we're looking for. When is this thing, this position function, equal to half the maximum height? Half of 180 is my 90. All right, so we can figure this out. When does this happen? Again, this is just solving for the t. You would need your calculator to do this. This is a calculator kind of problem. I would not expect you to do this by hand. And we would just solve for the quadratic here. It's going to happen at two different equations. Remember, this thing goes up and then it goes down. All right, it goes up into the air and then it comes down. If you calculate this, and if you want to get a quadratic function program for your graphing calculator, please let me know. I can either show you one or help you get one on your calculator. But those two answers are 4.393 seconds and 25.607 seconds. You can also get that simply by using the grapher on the TI. And how long was the rock aloft? Well, if we think about this, it says it goes up from the surface of the moon. So it's starting at the surface of the moon. We want to know when this thing is equal to 0. At time 0, it's obviously going to have a height of 0, but when else is this going to happen? Again, this is a really easy problem to solve. It's solving a quadratic, but this time we can factor out a t. All right, it happens when t is equal to 0, but that's not how long the rock was aloft. We want the other time, when it actually hits the ground. That happens when I solve this other part, when I solve this part of the equation. When does that equal 0? That happens at 30 seconds. And there's number 1. All right, moving on to number 2. The accompanying figure shows the velocity. Now, we really haven't looked at anything other than velocity graphs. Maybe we've looked at a few position graphs, but mostly we've just been looking at velocity graphs. I cannot emphasize how important it is for you guys to make sure you know what it is you are looking at. This could just very well be a position function, but instead it's a velocity function. Or we could be looking at an acceleration function, especially as the year goes on. This is so important that you recognize what it is that you are looking at. So this first question is asking, and I'm going to scroll down. I'll try to scroll back up and down. Sorry, this is going to be, I won't have it all in the screen at once. I'm sorry about that, but that's okay. The first question asks, when does the body reverse direction? The body is going to reverse direction when velocity changes sign. When does the velocity change sign? That happens here, and it happens here. That's when our velocity changes sign. That's when our thing reverses direction. It goes from heading in a positive direction, so the velocity here is positive, and down here the velocity is negative. So where does it reverse direction? It reverses direction when it changes from having a positive to a negative velocity, or from having a negative to a positive velocity. So that happens at time 2 seconds, and also at 7 seconds. Those are the 2 times when that happens. The second question is going to ask, when is the velocity moving at a constant rate of speed? When is the body moving at a constant rate of speed? And I know you can't see this in my screen right now. Let me see if I can change that quickly. Sorry. Oh yeah, look at that. I'm like a technology wizard. When approximately is the body moving at a constant speed? It's going to be at a constant speed when the velocity is constant. All right, it's so tempting to say that the thing isn't moving at all right here, but remember, it's just moving at a constant speed. It's moving backwards or to the left at that time, but our velocity is constant. Another way to think about this, and maybe a better way to think about it, is this is going to happen when acceleration is 0. And remember, acceleration is just the slopey slope of the tangent lines to velocity. All right, so the slopey slope there from here to here, all right, or using my little hand, from here to here, from 3 to 6, we're moving at a constant rate of speed. Okay, so from time 3 to time 6. Then tells me to graph the body's speed on the same graph in a different color. Remember, speed is the absolute value of velocity. Speed is the absolute value of velocity. So it's always going to be positive. This is just going to always be positive. This thing is going to go up to a value of 4, and then it's going to go along. Oh, that's just 3. I'm sorry, that's just 3. I can't read well sometimes. That's just going to go up to 3. This thing is going to go down. And then this piece is going to be exactly the same. So speed is just the absolute value of velocity. So all negative values become positive, and all positives stay positive. Graphing the acceleration, we're going to graph the slopes of the tangent lines. The acceleration, when I look at this first part, I'll just focus on this first part. The acceleration is constant there. Why is it constant? Because the slope of the tangent lines is the same. This is a piecewise linear function. If you thought about how you would write a function that defines the velocity of this body, you would write it as a piecewise linear function. And so I'll do, let's do acceleration in purple today. That'd be exciting. All right, we're going to take the slope of this line. The slope of the line is 3. Oh, I was a little too close to red. Not a good choice, not a good choice. Then we're going to have a slope of our tangent line, of -3. And then we're going to have an acceleration of 0. We already talked about that piece. And then we're going to have a slope of 3 again. And then we're going to have a negative slope. I don't know what that is. That's -1.5, it looks like. -1.5. All right, so that's my acceleration. That's the graph of the derivative of velocity. Remember that the derivative of velocity is acceleration. Okay, good job. All right, let's keep going. All right, a body's velocity at time t is equal to seconds. At time t seconds is v of t is equal to 2t to the third minus 9t squared plus 12t minus 5 meters per second. Find the body's speed each time the acceleration is 0. So first thing we got to do is figure out when our acceleration is 0. To get acceleration, we're going to take the derivative of the velocity to get the acceleration. Our acceleration is 6t squared minus 18t plus 12. We got to figure out when is acceleration equal to 0. So let's solve this thing. We can factor out a 6. And this happens at t is equal to 1 and t is equal to 2 seconds. I feel confident that you could all do that. So this happens at t is equal to 1 and t is equal to 2 seconds. All right, so what are they asking for? They're asking for the body's speed. So we want v of 2 and we want v of 1. We're going to take that 2 and we're going to plug it into that velocity equation. When we do that, we get negative 1. And when we plug in the 1, we get a value of 0. But remember, this is asking for speed. Speed is always positive. So our speed at t is equal to 2 is 1 meter per second. And our speed at 1 second is 0 meters per second. Right? Number 4 is a very similar question to the one we just did, so I'm going to do this much faster. The accompanying figure shows the velocity there. When does the particle move forward? The particle is going to move forward, and I'll just write this quickly. When v of t is greater than 0, it's going to move backwards. When v and t is less than 0, it's going to be speeding up. When v and a, velocity and acceleration, have the same sign. And it's going to slow down when velocity and acceleration have a opposite sign. You can be speeding up in a negative direction, remember. So when does this happen? When does it move forward? It moves forward between 0 and 1, and then again between 5 and 7 when our velocity is positive. It's going to move backwards when our velocity is negative. That on this graph is between 1 and 5. Notice between 1 and 5, the velocity is negative. When's it going to speed up? When v and a have the same sign. So when do v and a have the same sign? Well, between 1 and 2, let's look at what's happening between 1 and 2. The slope of the tangent line, or the derivative, is negative, as is the velocity is also negative. So that's going to be one time when this happens. And it's also going to happen again between 5 and 6. Between 5 and 6, so here to here, between that time 5 and time 6, both velocity and acceleration, the derivative of the tangent line, the slope of the tangent line and the velocity are both positive. All right, when do they have different signs? Well, this is going to happen between, and I know I'm speeding up here, this is 0 to 1, 3 to 5, and 6 to 7. Hopefully you can see why. If you understood why they have the same signs, you should understand why they have opposite signs. When is acceleration positive, negative, and 0? This is simply looking at the slopes of the tangent lines. So the slope is positive from 3 to 6. Let me take these marks off. Between 3 and 6, my slope is positive. That means my acceleration is positive. When is my slope negative? My slope is negative between 0 and 2 and 6 to 7. And when is this thing 0? Well, I don't know if you guys could read that on this graph, but between 7 and 9, it was intended for it to show it as 0 as well. So that would be between 2 and 3, and also between 7 and 9. When does it move at its greatest speed? It's going to be when the velocity is greatest, when it's farthest away from the x-axis. That happens at 0 and from 2 to 3. I don't really care if you include this point, but it does start off there at 2, and then it goes down to negative 2. So up at 2 and down at negative 2. It's at 2 meters per second is its speed at both of those places. And when does the particle stand still for more than an instant is from 7 to 9. Okay, last question. How fast is the water running out at the end of 10 minutes? If you see a question that asked how something is rate of change, this is a rate of change question. How fast is the water running out? This is me running out of time on my free YouTube account. All right, Q prime of T is equal to negative 8,000 gallons per minute. What is the average rate of change? Well, that's just A rock. You're going to do Q of 10 minus Q of 0 all over 10 minus 0. At the buzzer, negative 10,000 gallons per minute. Peace!